Hello, I just wanted to make this quick video for those of you who are interested in math, showing how MRI, and in particular image formation, works from a mathematical point of view. So as you recall, we place the person or object to be scanned into a very large magnet, and this magnet aligns the spins of the hydrogen nuclei. Now this creates a net magnetization, M, and this is basically the goal of MRI. That's what we want to measure. So what do? First thing is we send in a radio wave that tips the magnetization into the transverse plane. And then in order to encode the position, we add a magnetic field gradient. So what does this gradient do? The magnetic field gradient changes the relative phase of these spins. So we can represent that here with this multiplying up by e to the I phi. So we're changing the phase of the magnetization vector. So what is this phase? Well, change in phase over change in time is frequency. So that means the phase is the integral of the frequency over time. And as you recall, the frequency is directly proportional to the strength of the magnetic field, omega equals gamma b. So we can just substitute that in there. Now, what is this magnetic field? Well, in this case, I was saying we're applying a magnetic field gradient. What is a gradient? Well, that's just the change in the magnetic field over a particular position, dB dx. So rewriting that for a linear gradient, we can write that the field B is just g times x. Nice linear gradient, so we substitute that in, or g dot x. And now, assuming that the person is not moving, that is, x is not varying with time, we can take that out of the integral, and we're left with this equation here, x dot the integral of gamma g dt. Now we can just call this something else. For example, we could call it k. And so this simple equation here, we can just rewrite as m of x times e of I x dot k. Okay, so that's the effect of these magnetic field gradients. Now we want to collect that signal with the radio frequency coil. What does that radio frequency coil do? It sums up the spins over the entire space, right? It just collects the data wherever it is in space, it collects it, and essentially we see the sum of all of the spins. So mathematically, we can represent that with an integral. Now, for those of you who have taken some upper level math classes, you might recognize this particular equation. Yes, this is the equation for a Fourier transform. So by twisting up these spins using magnetic field gradients and then summing them up using an RF coil, we've created a Fourier transform. And so if our goal is to get this m of x from the signal that we've collected, we simply have to apply an inverse Fourier transform to the signal, and then we can get m of x. So I think this is kind of neat because it's really how, using actual electronics and physics, we can create this mathematical Fourier transform, or in other words, as a way of understanding why we have to apply a Fourier transform to the signal that we acquire in order to get our image. Now this mathematical formulation, and in particular knowing that k is equal to the integral of gamma g dt, is also really useful if we want to understand how we're acquiring the signal using a concept called Kspace. That is, we're collecting the images, we're collecting the signal in the spatial frequency space. And so if we sort of sketch out what the different linear magnetic field gradients are doing in the x, y, and z directions, knowing that k equals the integral of this gradient over time, we can use this to trace out how we're acquiring the data across Kspace. Or similarly, we could come up with other ways of traversing through Kspace and then turn that into the gradient waveforms that we would need to create